Hi. Today we're going to talk about atomic and ionic radius, which are one of many fallouts of the structure of the periodic table as we know it today. Jumping right into it, one of the first things I want to talk about is something we've already talked about as a class. What we have here is one of the groups was kind enough to lend me their graphs. We're looking at this is group one here, and this is period 2 here. So here we're going from top to bottom, and here we're going from left to right across the periodic table. And you can see as you go down the group, atomic radius increases, and as you go across the period, atomic radius decreases. This should be confusing to you because whatever reason you might think of that's causing one of the graphs, the other one seems to disagree. So this is what we're going to talk about today. Before we get too far into the conclusions, I'd want to build up some ideas behind it. So to look down a group, here I've copied a Bohr atom for lithium, and this is a Bohr atom for rubidium. What we have here is 3 protons, 4 neutrons, and then our electron configuration is 2-1. And then for rubidium, we have 37 protons. We've got some number of neutrons, although we're not going to worry about isotopic effects. I almost said 4 neutrons again. And then our electron configuration is 2, 8, 18, 8, 1. So again, these are both found in group 1 because their valence electrons are the same number, 1 each. And it does seem to be that rubidium is larger because there are more occupied shells. I know that we should maybe be talking about the wave mechanical model as the most modern model of the atom, but like I said in that video, I think it's easier, instead of drawing a bunch of overlapping clouds, to just stick with the Bohr atoms, because this gives us enough of a ground to have a conversation on. But yeah, more occupied shells means that the distance from the nucleus to the outermost electron is just flat out longer for the rubidium. And I did try to draw this, or get the two images somewhat to scale. It seems to be that the rubidium atom is about twice as large as the lithium atom, and I'm trying to show that. So this is pseudo to scale. But this makes sense. The more electron shells you have, the more particles you have, the more space it takes up. That said, it does seem to be the case that as we go across a period from beryllium to carbon to fluorine, I know they're out of order. This is the image I found. It does seem to be that the atomic radius decreases. This is what table S tells us, and there are your numbers. So how is it that we're getting something going on where here we've got, again, 4 protons. Here we have 9 protons. And here we have 6 protons. We could count up the neutrons, but again, they don't matter. Here our electron configuration is 2-2, here it's 2-7, and here it's 2-4. And to look at these, it does seem to be the case that as you put more stuff into the atom, it gets smaller, which doesn't really make any sense to me. Unless you talk about something called shielding and the impacts of shielding. When you have shells or even clouds of electrons, the clouds and the shells, they have a finite limit to their size. The first energy level takes up a certain amount of space. The second is further away from the nucleus. We've already established that. You can see that in your reference tables, right? Like we've got the idea of how big those atoms are as you add electron shells. In a completely Coulombic macroscopic sense, there's a force felt between the nucleus and the electrons. But when you're talking about this outermost electron, there's more than one force as soon as you have multiple electrons in the nucleus. There is an attraction between the electron and the nucleus, but in 2 ways. There's a repulsion between the 2 electrons, and, if you want to look at it this way, it's almost like the electron is kind of blocking some of that attraction from the nucleus. If this was, for example, an excited lithium, you would have an electron configuration of 1-1-1, And then somewhere elsewhere, you've got 3 protons. Yeah, it might look like this electron is misaligned and nothing's going to block it, but remember that these are electron clouds and that this electron is loosely associated with this whole region. So in a way, it's kind of like there's an electron in between the nucleus and the outer electrons, and it's canceling out some of that shielding. I would say that this electron here, that I'm circling in this blue color, feels the full nucleus. I would say that because of the presence of an electron cloud, this second layer electron feels less of a pull to the nucleus. This is kind of supported by the fact that it's further away, but it goes more than that. It's not just that it's further away, it's that there's also an inner electron playing defense. And then finally, to look at this outermost electron here, this is feeling the least amount of pull. And for most intents and purposes in this course, after today, we're really only going to focus on what forces, if any, are felt at the valence shell of the atom. So I'm most concerned with this electron, and I'm least concerned with the inner ones. To put a number to it, the term we're going to use is effective nuclear charge. We know what nuclear charge is. That's due to the protons in the nucleus. And it's represented by the letter Z, capital Z. That's this letter here. So that's your number of protons. And we're going to use N to represent all inner electrons, inner being anything that's not the energy level we're focusing on. So to calculate the effective nuclear charge, first we have to figure out the nuclear charge. I picked 3 different atoms here. This is boron. Boron has 5 protons, so Z equals a plus 5. For chlorine, Z equals a plus 17. And for copper, Z is a positive 29. Just to talk about the valence shell, I'm going to circle all of what we would call inner electrons. That is everything but that outermost occupied energy level. Here we've got 2, here we've got 10, and here we have 28. So your effective nuclear charge here is going to be equal to 5 minus 2 and plus 3. The effective nuclear charge is 17 minus 10, or plus 7. And then here, our effective nuclear charge is 29 minus 28, which is a plus 1. So let's go back to the previous slide, a couple previous slides, and let's add some new information here, and maybe this would help illuminate why we're seeing what we're seeing. Let's calculate the effective nuclear charge on the valence shell for each of these atoms. So for beryllium, your effective nuclear charge is going to be that you have 4 protons, there are 2 shielding, which gives us an effective pull of plus 2 on this electron. For fluorine, you're going to have 9 minus 7, which is equal to 9 minus 2, which is equal to a plus 7. And then for carbon, you get a plus 4. Oh, well, this is interesting, because now we can say, well, look, there is a number that seems to correlate directly with the atomic radius. It seems to me that as you add more protons, the nuclear charge goes up, but as you're adding electrons in the same period, those electrons are not filing in a blocking position, they're filing in a adjacent position, and they're not really shielding the rest of that valence shell. In this beryllium atom, this is getting pulled with a plus 2, this is getting pulled with a plus 7, and this is getting pulled with a plus 4, and the strength of the pull helps dictate the size. The stronger the pull, the smaller the atom. The one thing I will say to put a cap on all of this is exactly what it says here. We're going to say as a rule that electrons that are in the same energy level as whatever you're considering don't effectively shield each other. That is to say, you have 7 electrons in the chlorine outer shell. Those 7 electrons don't shield each other. It's the 10 inner ones that shield that whole shell, so to speak. So this kind of lines up the trend that we see, it seems that the atomic radius decreases as we go from left to right, and atomic radius increases as we go from top to bottom. Again, we've got 3 occupied shells and 2 occupied shells. Here, the effective nuclear charge is +1, and here the effective nuclear charge is a +2. There's more pull on a beryllium's valence shell than on a lithium's valence shell. Hypothetically, you could try and make some diagonal comparisons, but I'm going to say in certain directions it's a bad idea. Looking at, we could compare sodium to beryllium. You've got an extra energy level and a weaker effective nuclear charge on the valence shell, so I think sodium is going to be a lot larger than beryllium. But for magnesium, there's an extra valence shell, there's an extra electron shell, but the effective nuclear charge is larger. So you can make comparisons from upper right to lower left, but don't make comparisons from upper left to lower right. It just gets confusing. Speaking of confusing, we know that atoms gain and lose electrons to become ions, so it would be a good idea to talk about how the size of an ion compares to that of an atom. First, we're going to talk about cations. Cations mean positively charged ions, and to become a positive ion, an electron leaves the atom. And what's left behind, it appears to be, is smaller than what you started with. Consider the Bohr notation for sodium and for the sodium ion in the ground state. It seems that we have lost an entire energy level. Yes, the valence shell is still there. If we wanted, we could put a 0, but it's unoccupied. And if we measure the radius of an ion as the nucleus to the outermost electron, then the sodium ion is going to be way smaller than the sodium atom because we're not measuring to the 3rd energy level, we're measuring to the 2nd. And just to look at these images, they're not exactly to scale, but it does seem to me that as we go from 282 to 28, as we lose 2 electrons, the effect is amplified. So higher charge, smaller ion. Now that is to say higher positive charge, smaller ion, because we're only talking about cations in this case. The reason why the magnesium ion is smaller than the sodium ion in this case is because don't forget that the magnesium ion has 12 protons in its nucleus and the sodium ion has 11. So if they have the same electron configurations, 2,8 and 2,8, those 8 electrons are being pulled in by 11 protons versus 12, and obviously 12 protons pull with more force, yielding a smaller ion. The effect is reversed for anions. As they gain electrons, they get larger. Now, this is slightly less intuitive. The atomic or the Bohr notation for the electron configuration for chlorine as an atom is 287, and the chloride ion, which is the anion formed when chlorine gains an electron, is 288. It might make sense to say if you had, say, a helium atom becoming a helium anion, that you're going from 2 to 2,1, right? You're adding a whole energy level. So of course that would get larger. It might be slightly less intuitive that the chloride ion is larger than a chlorine atom. However, don't forget that I said that valence electrons don't effectively shield each other. There is still a small shielding effect, and if you want to consider it, if you go from having 7 electrons to having 8, I know I'm drawing for fluorine, but you know, same idea. There will be a certain amount of repulsion between these electrons, small though it is. Adding an electron into the same energy level causes larger repulsion. With the same amount of protons in your nucleus, but a larger repulsion, you'll have a larger ion. As you may guess, the anion effect also scales with magnitude of charge. So really, the safest thing to say is that the ion's absolute charge is what dictates its size relative to the atom from which it was made. I'm not comparing like super different things. I'm not talking about a potassium +1 ion and say an oxygen 1- ion. Like there's sometimes they're too far away to make a valid comparison. So to sum things up, radius is determined by 2 things: the number of shielding shells you have and the number of protons in your nucleus, which Both add up to give you your effective nuclear charge, which is just calculated by the number of protons minus the number of inner electrons. You can calculate effective nuclear charge on other levels than the valence, but we only focus on the valence. Atomic size decreases as you go from left to right and increases as you go from top to bottom, which means the smallest elements are going to be found in the upper right-hand corner, and the largest elements are going to be found in the lower left-hand corner of your periodic table. In general, it seems to be, to me, that atoms of nonmetals are small and atoms of metals are large. When making an ion out of your atom, the cations are always smaller than what you started with, the anions are larger, and that effect grows with the greater absolute magnitude of charge. Thanks for watching.